We will now discuss an important and interesting phenomenon in nature called resonance. What does the word resonance mean? Have you ever heard somebody saying, yes, what he says resonates with me? What it means is that I tend to agree with him. Now, resonance in nature has the same meaning. Two things seem to agree with each other. Now, what is resonance and when does it happen? Every object has a natural frequency of vibration. What does that mean? Every object has a natural frequency of vibration. In other words, you cannot, if you have a tuning fork here, this tuning fork has a natural frequency. I cannot change the frequency by hitting it hard. If I hit it hard, the amplitude will increase. But its natural frequency will not change. Every object has a natural frequency of vibration. Now, let me see if I can show you some examples. Now, here I have some objects. I'm sure you can see these objects. Now, each of these objects has a natural frequency. You can see this mass, when I hit it, no matter how hard or soft I hit, the frequency will not change. Look at another object. Its frequency will remain the same. That is its natural frequency. Now, look at these beakers. I can produce musical notes on it. You see that? Each of these, look at these two beakers. They are both of the same size, but I have water in one of them. That means its natural frequency, listen, is different from the natural frequency of this. Don't they sound different? They are different. So each object, every object has a natural frequency of vibration. Now, I'm sure you have come across a swing in a park. Now, suppose this is a swing in the park. Now, you keep a child on the swing and give the child a push. And as the child comes back, you give another push. What happens with time? Now, the amplitude of vibration keeps increasing. The child goes higher and higher. Now, this is resonance. Now, I told you resonance means agree. Now, what is agreeing with what here? This pendulum or the swing has a natural frequency. Now, that means when I set it into swinging, its frequency will be a constant. It has a natural frequency. Now, it just came to a stop. Now, every time the swing comes back, I'm going to give it a little force or a little push. And look at this. The frequency of the push and the frequency of the swing are exactly the same. Now here, the two things are agreeing. What are the two things that are agreeing? The frequency, the natural frequency of the swing and the frequency of the push that I give are agreeing. What happens therefore? The amplitude of vibration keeps on increasing, and here you have a resonance. Now, what happens instead of giving that force every time the swing comes back? If I go in between, look at that, I try to give a force here, well, I will stop the swing. It doesn't agree. Now, the force must be given at the end of every swing. Only then will the natural frequency of the swing be equal to the frequency of the push. That means resonance occurs when? When will resonance occur? Can you tell me what is the condition for resonance to occur? In order that resonance may occur, you need to impose a frequency on an object. The frequency of the imposed force must be equal to the natural frequency of that object. Then that object will vibrate with increasing amplitude. You see that? Now, have you ever heard of an opera singer shattering a glass? I have heard about it. I have seen it happen. Now, you know, suppose this is the glass. It has a natural frequency. Suppose I am the opera singer, which I am not. Opera singer can produce frequencies of, in fact, very many frequencies. You know that an opera singer can produce very high frequencies? Is that right? Ah! Okay. If one of the frequencies produced by the opera singer equal to the natural frequency of this glass or beaker, the beaker will vibrate with increasing amplitude, and finally it wouldn't be able to stand it anymore. It will shatter. Now, there are many other examples of resonance in nature where the natural frequency of a vibrating object agrees with an imposed external force. Have you ever heard of a bridge collapsing when a battery of soldiers marching on the bridge? You know that a battery of soldiers marching on a bridge is equivalent to imposing a periodic force on the bridge. You see, there are soldiers going like this, left, right, left, and so on. The bridge is made to move back and forth. Now, this is an external force. If the natural frequency of the bridge equal to the frequency of that external force, the bridge will oscillate back and forth with increasing amplitude. And by the time the soldiers reach the middle of the bridge collapses. In fact, many instances like this happened during World War I. And therefore, during World War II, soldiers, while crossing a bridge, were asked to disperse and not to move in formation. Well, look at the wonderful phenomenon of resonance. So, if I ask you for a definition of resonance, what would that be? What is the definition of resonance? In mechanical system, if a vibrating object is subjected to an external periodic force, where the frequency of that external force equal to the natural frequency of the vibrating object, the object will vibrate with increasing amplitude, and that is what we call the phenomenon of resonance. Well, we have actually seen the phenomenon of resonance. I had demonstrated to you the formation of stationary waves on a stretched string. Do you remember that? Or standing waves. Well, the formation of stationary waves on a stretched string is due to resonance. I'm going to demonstrate that to you one more time. Let's recall some of the principles we discussed in connection with stationary waves on a stretched string. You can see this stretched string has a natural frequency. From our discussion, you know that the natural frequency, the fundamental frequency we call it, depends on the length of the string. Now, this string is now subjected to an external force. You see, just like the swing was pushed each time it came back, this vibrator is actually applying that external force. Now, if the natural frequency is the same as the frequency of the mechanical vibrator, then the string will vibrate or will resonate with that frequency. When resonance occurs, the string will vibrate with maximum amplitude. Well, I can adjust the frequency so that by the time the energy goes to the fixed end and comes back, a fresh energy is made available. That is what we say the natural frequency and the imposed frequency agree. You see, just the same way the swing comes back, you apply the force. The energy of vibration goes to the end and comes back, the new force is created. Just like you keep pushing this mechanical vibrator, keep generating more energy, by the time the energy gets back, it must be synchronized. You see, the natural frequency of the string must be equal to the frequency of the imposed force. Now, at the moment, the natural frequency is not equal to the frequency of the vibrator. But I'm going to change the frequency of the vibrator and see what happens. All right, I'm changing the frequency. There you got resonance. You see, look at the resonance there. The string is now resonating with the frequency of the imposed force. That means when the energy of vibration travels all the way to the end and back, the fresh energy is created. And there is resonance between the two. Now, this is the fundamental frequency. That means the string will vibrate with a frequency equal to its fundamental frequency. I have the frequency value here I can read is 13 Hertz. That means this vibrator, mechanical vibrator, is moving up and down 13 times. And that is a measure of the fundamental frequency of the string. You see, the string will also resonate with twice the frequency here. Is that right? If it resonates with 13 Hertz, it should resonate also with 26 Hertz. That means by the time the energy goes to the end and comes back, a fresh energy will be available. I'm going to increase the frequency to 26 Hertz and see what happens. What I would like you to see is when I increase the frequency, say this is 18 Hertz, there is no resonance now. But as I increase it to 26 Hertz, look at the resonance. That is the beautiful resonance at 26 Hertz. Now this means the frequency of the oscillator or the vibrator is twice the frequency of the string, twice the fundamental frequency. Resonance will also occur if the frequency of the vibrator is 3 times the fundamental. All right? I'm going to make the frequency 3 times the fundamental, about 39. I'm going to increase the frequency. You notice now resonance has disappeared because the natural frequency of the string does not agree with the frequency of the vibrator. Is that right? Okay, I'm going to increase the frequency, see what happens now. All right, the frequency is now getting close to 39, and now you have resonance again. This is the third mode of resonance. The third mode of resonance. Now, can I get it right? I'm trying. There you are. So the third mode of resonance, I can now keep on going to the fourth mode. Let's see if we can get the fourth mode of resonance. All right, that is the fourth mode. Is that right? I think we passed that. There you are. That is the fourth mode of vibration. So this is a beautiful example of resonances in mechanical system. Let's look at this one more time.